What I'm now going to do is to derive the extended Kalman filter in a manner very similar to how I derived the linear Kalman filter in a recent lecture. So I'm going to start with the prediction of the extended Kalman filter. And then the key thing that we utilize as an approximation is Taylor expansion. Which goes like this. We are going to have the propagation function, the forward mapping of the process model of the previous state. We're going to approximate that as the function f applied to the previous estimate. And then a matrix f times the difference between the actual state at the previous iteration and the estimate. Then I make the assumption that everything to begin with is Gaussian. Of course, I cannot expect that to hold as you go through cycle after cycle, but I'm going to assume that. So the previous posterior of density of x, conditional on all the data from time step 1 up to and including time step k minus 1. So notice this is typically how I denote that, this column notation. So I assume that this should be given by a Gaussian with some expectation, which of course is the previous estimate, and a corresponding covariance. This is my assumption. And then I'm going to see what is the predicted density based on this assumption, and how can I express it using this Taylor expansion machinery. So the predicted density is the density of xk, again given z from 1 to k minus 1. And this is given by the Chapman-Kolmogorov integral. So I assume that they have a Gaussian, although nonlinear process model. So here we have the nonlinearity in the process model, this lowercase f. And then I have the process noise in the Gaussian noise model. So this I'm going to multiply with the previous posterior and integrate it. Okay, so then I'm going to use my linearization approximation. So I keep this xk here, but then this I'm going to now split up into lowercase f of the previous estimate plus capital F times delta x k minus 1. Then I'm going to do, now I need to get these delta x's ready to work with them. So I'm going to do the same thing here, this xk minus 1. I can also split that up into the previous estimate plus delta xk minus 1. So this is by definition equal to this sum. And then I still have the same expectation and covariance. Now there is no xk minus 1 anymore, so I can't integrate over that. But clearly there is a linear relationship between xk minus 1 and delta xk minus 1. This one doesn't vary. This is the one that varies. This is the unknown thing. So I can just make a trivial substitution. So d delta xk minus 1. And then so the next step is to move things a bit around in here so that I can use the product identity. That means that in the expectation slot in the first Gaussian, I want to have this thing alone. So this thing I need to get rid of. How do I do that? Well, it's very simple. I move it over to the random vector slot. And then I do the similar trick here. I move this thing over there to the expectation slot so that I'm left with a delta. And clearly this is the same as this, so it's going to cancel, and I'm going to be left with delta xk minus 1 here and 0 in the expectation slot. And nothing much happens to the covariance. And then I can use the product identity. So the integration then disappears when or rather I can take the first Gaussian that I get out of the product identity out of the integral. So this is the Gaussian I am looking at now. So we remember from the product entity that the first random vector in the first Gaussian remains unchanged. Nothing happens to that. Then the expectation in the new first Gaussian should be this matrix F times the expectation of the second original Gaussian. F times 0, that's 0. And then the covariance of the first Gaussian that comes out of the product entity should be this matrix times this matrix transpose plus this matrix. And then I have a Gaussian in this delta x that comes out of the product identity. So that one we still need to integrate over. And then there is some expression for whatever is inside this Gaussian, which I don't need to think about since I'm just going to integrate over it anyway. And the integral of Gaussian over the entire state space is 1. So this whole thing disappears. So then I'm left with this, and then I just need to move things a bit around to get this back to the form where that makes a bit more sense. So I keep this xk here, but now I can move this back over here. And nothing happens to the covariance. So that was the EKF prediction. And you see the key trick towards deriving it this way as I did is just to recognize how you can move things back and forth between the random vector slot and the expectation slot. While I'm at it, let me just do the update as well. I'm not going to do that to the same level of detail, but I'm going just to show that the same principles can be used there as well. So for the update, we have again a Taylor approximation, Taylor expansion. Now it's the nonlinear measurement function that we need to expand. First order expansion. Do it around the prediction that would be this thing. Then I have a matrix times some delta xk. So of course delta xk is the same as xk minus the prediction. Now I know of course that what I did here is an approximation, but I'm nevertheless going to assume that I have a Gaussian to begin with. So I assume that my predicted density, P of xk given z 1 to k minus 1, That is a Gaussian. With an expectation and a covariance. Then let's just dig into the posterior density. What will the posterior then be and what can we approximate it as? So it's P of xk given z1 to k. Then we always find the posterior by means of bias rule, so I write a proportionality symbol. And then we have two Gaussians. We assume that we have Gaussian noise. So this is a bias applied to the model that we use for the extended Kalman filter. So Gaussian model, but nonlinear function in here. Then I'm going to go straight into the approximations. So I'm using the same trick. I do it a few steps now together. So I've done the tidal expansion and just moved my h of the prediction over to the other side. And then I can use the same trick as I used over there just to get delta x here and a 0 expectation for the second Gaussian. K given k minus 1. And then I have this on a form where I can use the product identity. So I'm going straight into that. Then I have some Gaussian first that, well, it does not depend on delta x. So I can ignore this Gaussian, same as what I did for the standard Kalman filter. And then I have a second Gaussian that is in delta x. So it has to begin with expectation 0, but then I had to add this correction, Kalman correction. So then it's going to look like this. So when I do the Kalman correction here, I'm going to end up taking this and subtracting h times this expectation, which is 0. So that was the Kalman correction, and I need a new covariance, which is given by the same formula as before. And this is proportional to a Gaussian that looks like this. So what I've done here is, I should explain this in a bit more detail. Let me just write it like this. There is something that I multiply this W with. I'm not going to bother to write that all the way out. So you recognize what I have in this Gaussian as what I had in the second Gaussian here if I just move this around, except from these prediction terms that I suddenly introduced. But I can do that. I can add the same thing in this slot as I can do in this slot, because when I calculate the Mahalanobis distance in the Gaussian, I'm just going to subtract these. So I'm free to do that. And once I've done that, I can immediately recognize this thing as nothing else than xk. And then on the other side, well, I'm just going to have what I have. So let's now write this completely out. Zk minus h of the prediction. So then I have the Gaussian, that posterior Gaussian, and approximation of that. That is what you use in the extended Kalman filter. So just a comment on this, the way I address this, I kind of like to do it what really made me fall in love with the product identity is that it's very handy when you're dealing with this kind of mildly nonlinear systems to work systematically with something like this. You could probably derive all of this without using the product identity, but it becomes so neat and systematic when you use it.